Hello, Mr. Snell here again. We're carrying on with moles. Hopefully, by now you're starting to feel a little bit more confident, but there are a lot of calculations. When we put it all together, it will make more sense than it does sometimes as you go along. When you're revising things or getting to know a subject, what you find is that at first it feels like there are an awful lot of little bits and pieces and they don't seem to sit together. They will eventually, I promise. Today, what we're going to do about is empirical and molecular formulas. Now, you know about formulas, you probably know about formulas, but I need to tell you about empirical formulas. It's really fairly simple stuff. The idea is this: a formula, a molecular formula, should tell me the number of atoms of each element in one molecule of the chemical. So most people will know that carbon dioxide is CO2. One carbon, two oxygens. Most people will know that glucose is C6H12O6. But a machine trying to analyze a chemical, a white chemical, will not necessarily know that it's C6H12O6. It will simply tell it the ratio of the carbon to hydrogen to oxygen. In other words, if I put in 2 grams of it, then into the machine, and the machine is analyzing it, then it will only tell me the ratio of the number of atoms in that 2 grams. It won't tell me how many there are in each molecule. What an empirical formula is the simplest ratio of atoms in a molecule. The simplest ratio. So my C6H12O6 wouldn't be perceived as C6H12O6 by the machine, but would be seen as C1H2O1. And so we need some way of finding out that in every one molecule, there's actually 6 carbons, 12 hydrogens, and 6 oxygens. So that's what this one is about. So let's have a look at it. What I have here is a little presentation again. This is about moles, and it's number 3 of the set of them. And it goes like this. It's about empirical and molecular formula, but it's also about using Avogadro's number, which is that big number 6.023 times 10 to the 23. And it goes like this. I just said that the empirical formula is the simplest ratio. So I took glucose, C6H12O6, and we simplify it, divide through by 6, we get it down to CH2O, and that's its empirical formula. But if we think that that is its molecular formula, we have a problem. So what we've got to do is we've got to think about how we get from one to the other. Firstly, let's have a go, and I want you to have a little bit of a go at this. What's the empirical formula of these here? H2O2 is hydrogen peroxide, CuSO4 is copper sulfate, C2H4O2 could be all sorts of things, but in this case it's ethanoic or acetic acid, C6H6 is benzene, and H2SO4 you know as sulfuric 6 acid. Have a look at them. Simplify and work out what the empirical formulas are. I'll give you a moment. Okay. H2O2 is going to be just HO. CuSO4, we can't simplify because we've got 1 here. We can't divide that down. C2H4O2 will divide by 2 and become CH2O, which is interesting in that this is the molecule that I was thinking of here was vinegar, ethanoic or acetic acid, and it comes out as the same empirical formula as glucose. We wouldn't want to make the mistake of adding the wrong one. This one here, C6H6, benzene is going to come out as CH, and H2SO4 is going to stay as H2SO4 because whenever we've got 1 atom, we can't divide that down. But we need to be able to calculate the empirical formula. And I've come up with this rather silly way of doing it. And it's using this doctor here, and it's using the statement, I'm Dr. Empirical, and you'll see how it works. We're going to use these 4 letters here. I'm Doctor, IMDR, and it works like this. The sort of question you get comes up with a percentage or a mass of the elements in a particular chemical. So this chemical here is 70% iron, that's its RAM or REM, and 30% oxygen, and its RAM is 16. What we do is this. We go, okay, I'm Dr. Empirical. The first 4 letters, IMDR, are to remind you of the order in which you do it. You write down the information, which will be as a percentage or a mass. Then you work out the moles, and that'll be using the green, the first triangle. Then you divide by the smallest one. If you remember, finding a ratio is always dividing by the smallest, and that gives me the ratio, or should give me the ratio, or close to it. We'll see an example where that comes up later, and then that will allow me the empirical formula. We normally do it as a little table. So IMDR goes down the side. I write down all the information I've got about the chemical. So Fe, RAM 56, 70%, oxygen, RAM 16, 30%. Moles, first triangle. The mass, if we imagine we've got 100 grams, 70% will be 70 grams. So 70 divided by 56, 1 1/4. 30 divided by 16, 1.875. Then we divide through, IMD divide by the smallest. Well, this is the smallest. So 1.25 divided by 1.25 is 1. And 1.875 divided by the same 1.25 is 1.5. Now, the reason we've got ratio here is because sometimes this will produce 2 integers, 2 whole numbers, and sometimes it won't. We can't have 1.5 oxygens. So we've got to find a way to turn both of these numbers into integers and do the same thing to both of them. 1.5, if I double it, becomes 3. So I double this one and that one, it becomes 2 and 3. So the empirical formula is Fe2O3. Fe2O3. Simple. So let's have a go at some. I'm going to ask you to pause this in just a minute. It should take you a little while. Just remember to set it up like this. IMDR, here's each of the chemicals. It doesn't matter whether there are more than 2, or maybe 5, it doesn't matter. Here, the first one, 52.2% carbon, there's its RAM, 13% hydrogen, 1, and the rest is oxygen. So you're going to have to add those together and take them away from 1, find its empirical formula. The second one, an oxide of copper is reduced to copper by heating with hydrogen. In other words, the hydrogen takes the oxygen away from the copper. Here's the mass before, 1.59, so that will be the mass of the whole copper oxide, and after heating it, it's 1.27. So that must be the mass of the copper, so this minus that will allow us the oxygen. So then you'll have the mass of the copper, 1.59 minus 1.27 will give me the oxygen. And here's aspirin. And this is where we move a little bit further. We're going to work out the empirical formula of the aspirin here. And then its RMM is 180. So what you do is you say, okay, I work out the empirical formula. Let's take the example of glucose. Glucose came out as CH2O. If that was the molecule, glucose would weigh 30. Carbon, 2 hydrogens, 1 oxygen weighs 30. But just like aspirin, slightly surprisingly, glucose has an RMM of 180. So 30 isn't enough. So we say, how many 30s are there in 180? That 180 divided by 30 is 6. So instead of it being CH2O, we know that glucose is 6 times that. In other words, C6H12O6. So you can do the same sort of thing here. I'm going to ask you to pause now, have a look at the questions, write down the question, have a go, see if you can answer it. And in a few moments, when you switch it back on, I'll give you the answers. So pause it now and have a go. And I'm back, and here are the answers. Okay, In the first one, we had 3 elements here. If you got C2H6O, you're right. If not, have a look at this, pause it for a minute. Just remember IMDR, moles, first triangle, mass over RAM. Mass over RAM, mass over RAM. Divide through by the smallest. The smallest is 2.175 here. So we got 4.335, 13, 2.175. Divide them all by this one, 2, 6, 1. So the answer is 2 to 6 to 1. And so 2 carbons, 6 hydrogens, 1 oxygen. Number 2, if you got CuO, you're right. If not, have a look at it again. Number 3, bit more difficult. So we get the carbon, the hydrogen, the oxygen. We work out the moles, 5, 4.44, 2.2225. Divide through all of them by the 2.2225. This is 2 1/4. This is 2, this is 1. Now to get that 2.25 up to a whole number, we would have to multiply by 4, which will make it as 9. That by 4 is 8. This is 4. So the empirical formula is C9H8O4. Now, if we look at that and we work out the RMM of that, we would find that it would be 9 12s, 8 1s, 4 16s, which would weigh 180. Now it told us in the question that the RMM was 180, so that's the M. That is the molecular formula. The empirical formula, just like something like CuSO4, the empirical is the same as the molecular. Okay. So the molecular formula is found from the empirical formula using the MR or RMM. So here's one, HO, the empirical formula. We work out what the mass of that is. We realize that the whole molecule weighs 34. So how many of these do we have? We don't put the number in front, we put it within this. So we multiply the hydrogen's oxygen by the right number. So it's simple. This one here, HO, would weigh 17. That's what we call the apparent RMM. The real RMM is 34. So we say, oh, look, it's twice that. So instead of being HO, it's going to have to be twice as many. And that makes it H2O2. So you take the real RMM, put it over what the empirical formula seems to weigh, and that tells me what I have to multiply all the empirical formula by. This is hydrogen peroxide, used for cleaning vegetables, purifying things, killing bugs on surfaces, and bleaching hair. Wow. Why isn't it 2HO? Have a moment to think. Well, that's because 2HO means 2 separate HOs. H2O2 means a hydrogen attached to an oxygen, attached to an oxygen, attached to a hydrogen, hydrogen peroxide. Okay, excuse me. So here are some to try. What I want you to do is to work out the molecular formula of each one of these. There's an empirical formula and an RMM. There's the RAMs, the ARs for the different elements here. So what we can do is just go, okay, work out that, divide this by the number of that, and work out what they are. Have a moment, pause the video just for a moment, and have a go, and then I'll come back with the answers in a moment. And I'm back. Here's the first one. The empirical formula was CH2O, the RMM was 120. Whoops. There we are. Oh, come on. And so if this here, the empirical formula is CH2O, that would weigh 12 and 2 and 16, which is 30. 120 over 30 is 4. So we need 4 times the whole of this. So multiply that by 4, this by 4, that by 4, C4H8O4. And the other answers come out as FES and twice that one, C2H4Cl2. All right. Now, this is a little bit more complicated. These are proper examination questions, but they're not that much more difficult. All you've got to do is remember to use one of the three triangles, whichever one you need, okay? Now, this one first is pretty simple, but it was worth the same number of marks as this much more complicated one. So what I want you to do is to have a go at it. This one here, a solvent, that just means a liquid which we dissolve other things in, is made from 54.55% carbon, 9.09 hydrogen, 36.36 oxygen, and its RMM is that. Find its empirical formula and its molecular formula. I don't know why that semicolon has turned up, it doesn't matter. 4 marks. Now that's a very simple question. This one is more complicated. A hydrocarbon means, as I'm sure you know, a compound containing carbon and hydrogen only. And it's got an RMM of 84, so it's telling me that originally at the start. It burns in oxygen to produce 2.88 cubic decimeters. Oh, hang on, that's a volume of a gas. So that would mean I'm going to use the third triangle here to work out the moles. And 2.16 grams of hydrogen, that's a grams, so I'm going to use the first triangle there. So in this one here, they should tell you, but 1 mole is 24 cubic decimeters for a mole of a gas, and hydrogen, water, H2O, has got an RMM of 18. So using the first triangle, it's 2.16 over 18. So you need to work out the moles of these two, and then that's done it, because that will give us the ratio we can find, slightly different from this type of question, and then you can find its molecular formula because they give you the RMM. Okay, have a go at those. I'll give you the answers in just a moment. Pause the video and have a go. And I'm back. So here's the, oops, sorry, that's another question. Here's the solvent. The solvent comes out as this. And its molecular formula is that. In the second one, its empirical formula is CH2, and the molecular formula is C6H12. You may well recognize that because it's twice the number of hydrogens as carbons. As an alkene, that's an alkene called hexene. Okay, this is the one that we did at the end of lesson 2. So this last bit here is one where we're using Avogadro's number. And this is one in which we have something slightly different to do. What we have to do is to work out how many moles there are of whatever chemical we're given, and then work out how many moles that would mean of that particular atom, and then multiply that by 6.023 times 10 to the 23. So this is a mass, and therefore I'm going to use the first triangle. So moles equals grams over RMM. So I'm going to go 4 grams over the mass of NaOH. They've made this nice because the RMM is 40. So it's 4 over 40, which is 0.1. And there's one Na in each one of these. So 0.1 moles of NaOH will produce 0.1 moles of Na. If 1 mole is 6 times 10 to the 23, then 0.1 is 6 times 10 to the 22. Try the same with these two here. I'll give you a moment, pause the video, and I'll come back to you in just a minute. Okay, here we are. In A, 4 grams over 40, 0.1. There's only one Na in NaOH, 0.1 moles of Na is 6.023 times 10 to the 22. You don't need to remember Avogadro's number, 6.023 times 10 to the 23 at all. That will always be given to you if you need to use it. In the second one, we have 0.0055 grams of calcium carbonate. CaCO3 has an RMM of 100. So it's this divided by 100, which is that. That 6 has turned up again from lesson 1. There are 3 oxygens. We're asked for the oxygens. There are 3 in each CaCO3, so it's 3 times this number there. And then you multiply that, that's the moles of O's, by the 6.023 times 10 to the 23, which is 1 times 10 to the 20. And the final question, how many atoms of hydrogen in 10 grams of sucrose? There's the hydrogen, there are 22 in every one. So when I've worked out the moles of sucrose, table sugar, cane sugar, then I know I'm going to have 22 times as many hydrogens. So here it is. The moles of sucrose are 10 over 342, that's the RMM, 22 times that, that's 0.6433 moles, multiply that by 6.023 times 10 to the 23, I get 3.874 times 10 to the 23, that's nearly 400,000 million hydrogens in only 10 grams. That's about 10 teaspoons of sucrose. Amazing. And that's the end of that. Lesson 3. Next time we will pull it all together and try and make it a little bit more coherent so that you get an idea, an overview of the whole thing. But that's me for today, and I hope it was useful. So just keep on sticking with it and it will make more and more sense. But for the moment, this is Mr. Snell saying bye. Goodbye.